engine running. We have a liftoff. Liftoff on Apollo 11.
Humanity has left Earth, walked on the moon, and sent machines beyond the edge of the solar system. But there is one place we still cannot reach. Not a galaxy, not even the edge of the Milky Way. Just the nearest star, 4.24 light-years away. A distance so small in cosmic terms, yet so large it breaks everything we know about travel. Because even if we left today, it would take tens of thousands of years to arrive. So the question is not where it is. The question is, why is it impossible? To understand that, we first need to understand what we are actually trying to reach. Because the nearest star is not just a single star. It is part of a system, a small group of stars bound together by gravity. We call it the Alpha Centauri system. Inside it, there is one object that stands out the most, a faint red dwarf star known as Proxima Centauri. And it is this star that holds the record for being the closest known star to our sun, just 4.24 light-years away. That number sounds small, but it is not. 1 light-year is the distance light travels in an entire year, roughly 9.46 trillion kilometers. Multiply that by 4.24, and you get a distance so large that numbers alone stop making sense. It is not just far, it is unimaginably far for anything built by humans. To put this into perspective, we need to look at what we have already achieved. The fastest human-made object ever launched is not anywhere near that speed. Even after decades of advancement, our spacecraft moves slowly compared to the scale of space. One of the most distant spacecraft ever built, Voyager 1, is now traveling beyond the solar system. But even at its incredible speed, if you aimed it toward the nearest star, it would take tens of thousands of years to arrive. That means, if Voyager 1 left Earth at the time of ancient human civilizations, it still would not have arrived yet, and would not arrive for thousands of years into the future. So why is it so slow? Why can't we just build faster rockets? The answer begins with something simple: energy. Every increase in speed requires an exponential increase in energy. It is not a straight line. It is not even a curve that is easy to manage. It is a wall that gets steeper the closer you get to the speed of light. And the speed of light is not just fast. It is the ultimate speed limit of the universe. Nothing with mass can reach it. Not rockets, not spacecraft, not even theoretical engines we currently understand. So the moment we say reach another star, we are immediately facing a limitation built into the fabric of physics itself. But speed is not the only problem. Space itself is not empty. It is filled with particles, radiation, and microscopic dust. At the speeds required for interstellar travel, even a tiny particle becomes dangerous. Something the size of a grain of sand could hit a spacecraft with the force of an explosion. And cosmic radiation, high-energy particles from deep space, would slowly damage both machines and humans over time. So even if we solve speed, we still face survival. Then comes another problem: time. Even if we built a spacecraft capable of traveling at a significant fraction of the speed of light, the journey would still take years, decades, or centuries. That creates a strange situation, because no human lifespan can naturally survive such a journey. A child born on Earth would grow old and die long before reaching another star. So we are forced into a difficult idea. Either we send machines that outlive us, or we design ships where humans are born, live, and die across generations. These are called generation ships. Massive spacecraft designed to support entire societies for centuries. But even this idea comes with problems, because over long periods of time, technology, culture, and systems may fail in unpredictable ways. A journey lasting hundreds of years is not just an engineering challenge. It is a civilization challenge. So we are left with a contradiction. The nearest star is close enough to imagine, but far enough to feel impossible. And this is where modern science begins to explore alternatives. One of the most serious ideas being researched today is not to send large spacecraft at all, but tiny ones, gram-scale probes, small enough to be pushed by light itself. This concept is being explored by projects such as Breakthrough Starshot. The idea is simple in theory, but extreme in practice. A powerful ground-based laser would fire energy at a thin reflective sail. This sail would push a tiny spacecraft to a fraction of the speed of light. At those speeds, it could reach the nearest star in just a few decades, not thousands of years. But there are still massive challenges. We have never built lasers powerful enough for this scale of propulsion. We have never tested materials that can survive that acceleration. And we have never successfully slowed a probe down after it arrives, because even if it reaches another star, it would fly past it in a blink of an eye. No stopping, no landing, just a fast flyby of another world. And that raises another question. What is the point of reaching another star if you cannot even stay there? This is where the problem becomes deeper than engineering. It becomes philosophical, because interstellar travel is not just about distance. It is about presence, about being there, about interacting with another star system, not just passing by it like a message in the dark. And yet, there are even more radical ideas. Ideas that exist only in theory. Concepts like nuclear fusion propulsion, antimatter engines, or even space-time distortion concepts such as warp drives and wormholes. These ideas suggest shortcuts through space itself, but none of them exist in a practical tested form. Some require energy levels far beyond anything humanity can currently produce. Others require forms of matter or physics we have never observed. So for now, they remain ideas, not solutions. So we return to the same conclusion. The nearest star is not unreachable because it is hidden. It is unreachable because everything we know about physics, energy, and time works against us. It is a distance that exposes the limits of chemical rockets, the limits of human lifespan, and possibly even the limits of early civilization itself. But there is another way to look at it, because sometimes impossibility is not a barrier. It is a timeline, a measurement of how far we still have to go. A few hundred years ago, crossing oceans felt impossible. A century ago, leaving Earth felt impossible. Today, both are reality. So the question becomes, is reaching another star impossible or just not yet possible? The universe is not static. Technology is not static. And humanity is not static. Everything we have ever achieved started with something that once seemed unreachable, and the nearest star may simply be the next version of that pattern, a problem waiting for a future version of civilization to solve. But there is still a deeper thought. Even if we never reach another star in our lifetime, we already know it exists. We can see its light. We can measure its distance. We can imagine what might orbit it. We can send our thoughts toward it at the speed of light itself. And in a way, we are already connected to it. So perhaps the real answer is not whether humanity will reach the nearest star, but whether humanity will continue long enough to eventually make the impossible normal. Because right now, the nearest star is not just a destination. It is a test of energy, a test of time, and a test of whether a species like ours can ever grow beyond the world that created it. And until that happens, the nearest star will remain what it has always been. Visible, measurable, dreamed about, but still